energy-based model for virtual creatures, please.
Yep. Thank you. Can you hear me? Yes, good. Yeah, so hi everyone, my name is Junior. I'm going to talk about energy-based models for virtual creatures. I think everybody here is familiar with virtual creatures, so but just in case, I'm going to show you some demos. And also, by the way, you can follow the presentation on this link. There are going to be some demos. I don't know if they're going to run smoothly in all computers, so I apologize in advance if this runs a little bit slow on your device, but you can follow the presentation here. So this is what I mean by virtual creatures. So we have some kind of simulation, but it's not just some like a basic passive simulation. We also have some active component to simulate things like muscle contraction, relaxation, like emotion, things like this. And this is driven by a physical simulation, but also there's a neural network that is controlling this agent. So there's a sensory motor control loop that is constantly sensing the state of the agent, and based on that, it produces muscle commands. And it's also robust to perturbations. This is not just like a periodic sequence of signals. You can see that the signals can actually adapt when I perturb the system. Um, and yeah, so it's relatively robust to perturbations. It can recover from those perturbations, and there's a lot of components here at play. So I'm going to use simulations like this to exemplify the concepts that I want to present here. By the way, this implementation is open source. You can check out this repo for the code. And I'm going to speak a little bit about this implementation in particular, but also more generally, I want to talk about more general principles behind this simulation that I think are probably generally applicable to many domains. So the idea is energy-based model. So what do I mean by this? I mean, we can understand the state transitions or the evolution of the system as an energy minimization procedure. And it's kind of unfortunate that energy is such an overloaded term. So energy can mean many different things in many different contexts. So I want to be very precise about what I mean by energy. I'm going to use energy in two senses. First, I'm going to use energy in the sense of potential energy, which has a very specific definition in physics, classical mechanics. And then I'm going to use the term energy in the sense of energy-based models, which is a branch of machine learning, where energy is used to refer to any scalar valued function that measures incompatibility between variables. And I also want to make some connections to scale-free cognition, which is this very interesting framework proposed by Michael Levin. And the main idea is that we should recognize there's a continuum of cognitive capacities that goes from just physics to what you would normally consider more conventionally intelligent agents. But even in things that we normally consider just physics, you can already see some kind of basal form of cognition. And I think this is important, especially in the context of virtual creatures, where we often see this pattern where you might say, yeah, I'm going to use this physics engine, and it's just the physics engine. Who cares? I actually want to work on the interesting stuff, which is like the evolutionary algorithm, the training method, the morphology optimization, whatever. I'm going to go the complete opposite here. I'm not going to say anything about that. I'm only going to talk about the physics engine. And I'm going to try to convince you that we should take the physics engine more seriously. And it's all about goal-directed behavior at different scales. And I think the physics engine already manifests like a very basal form of cognition. And it's all about goal-directed behavior at different scales. And the scale is given by the cognitive light cone, which is the spatial-temporal scale of the agent's goals. Okay, so let's start with more basic concrete concepts. So energy minimization. Like I said at the beginning, I'm going to use energy in the sense of potential energy very specifically at the beginning. So what you see here is a mass spring system. So you can think of this as a goal-directed system whose goal is to minimize its elastic potential energy. And it's also very robust to perturbations. So if I perturb the system, you can see the elastic energy goes up, but because this is a very competent agent at achieving its goal, which is minimizing its elastic potential energy, it can eventually recover can make the potential energy go down again. And because the elastic potential energy is a differentiable function, we can implement this with automatic differentiation. So we compute the energy, and then we run the backward pass or do backpropagation or some kind of automatic differentiation to compute the gradient of the potential energy with respect to the vertex positions. And we use that gradient to update the positions. That's it. So this is goal-directed behavior at a very basic level. And I'm trying to be careful here to not say anything about the force. The force is just the negative gradient of the potential energy. But the force is not important. I think that the important thing is the energy function. The force is something you just compute with automatic differentiation, and it's not very intuitive because it's a high-dimensional vector, which for very complicated energy functions might be very difficult to understand. Whereas the energy function gives you just a number. It's like the goal of the system in some sense. Okay, so this is just a mass spring system, but for the simulation that I showed you at the beginning, we have more components. So we have triangles, we have gravity, we have inertia, and many other things that I'm going to discuss in a moment. But as you can see here, I can also show this. There we go. So yeah, so I can also perturb the system. The elastic potential energy can also go up. And then because again, this is also just like a competent agent in a sense that can minimize its potential energy. The energy can go down. But we can also introduce this interface, these adjustable set points, these actuation mechanisms to do something like muscle contraction and muscle relaxation. And again, traditionally, the way people would describe this is by saying, well, you are exerting a force along a certain direction. No, well, yes, in a way we are doing that, but I would like us to think in terms of reshaping the energy landscape. So we are just dynamically changing the energy function. And because it's a very competent agent at minimizing that elastic potential energy, it's eventually going to find its way to that new local minimum. So we're basically reshaping the energy landscape, and this can find a new local minimum. Yeah. So this is just a detail, but I think it's a very important detail because I've talked a lot about mass spring systems, and sometimes people think that this is a mass spring system. This is not a mass spring system. So the springs are the pink segments that I showed you before, but these white triangles, these are not springs, these are actual triangles. So we can actually define energy functions at the level of triangles. And this is very important because that's not possible. We cannot achieve this level of robustness to deformations, to perturbations, just with springs. This is a mass spring system. And it's not just a matter of stiffness. I can increase the stiffness and yeah, it helps a little bit, but it doesn't really fix the fundamental issue. Even if I reset the simulation, you might think, yeah, okay, it's fixed. Not really. The problem is this is not a very competent agent at preserving its shape because as soon as I get it into these bad local minima, it won't be able to recover. So this energy landscape is full of bad local minima and the agent is not competent enough to recover its shape. In a way, this is like saying the springs have a very small cognitive light cone. They can only see two nodes. And to actually preserve shape, to actually measure deformation in 2D, we need a slightly larger cognitive light cone composed of three nodes at least. And that's how we define the triangle. So there's no global descriptor for the shape. This is all in a way distributed in every triangle. And we just define the energy functions at the triangle level. So yes, this is not a mass spring system. There are springs, but the triangles are also very important. And it's all about, in a way, scaling the cognitive light cone. So you can imagine scaling up the cognitive light cone even more to do things like locomotion, where we're basically exploiting these basal forms of goal-directed behavior, like potential energy minimization, shape preservation, and so on. Where you can think of this as the whole being capable of pursuing larger goals than the parts, but each part can still be seen as a very basic cognitive agent with a small cognitive light cone. And here's a quote from Michael Levin that I really like. The things that we call alive are the things that are good at scaling their goals and pushing them into new problem spaces. For example, from potential energy minimization to locomotion. So a few more details about the implementation. So like I told you at the beginning, this is all driven by minimization of energy or some function that I'm going to call energy. And it's composed of 6 energy terms: muscle triangles, gravity, collision, friction, inertia. Some of these are actual potential energies in the classical mechanics sense, which means that they are just functions of positions. But then we also have things that are a little bit trickier, like the muscle. The muscle, for example, depend on some action signal. We also have things like inertia, which depend on the previous state, expressed in terms of positions and velocities. And this is where the term potential energy is not appropriate. It's something else. And I'm still going to use the term energy because this is still consistent with the terminology from energy-based models in machine learning, where the energy function is just a scalar valued function that measures incompatibility between variables. And the way we use this function is to do the minimization required to update the system. So what I actually implement in the simulation to update the system one step forwards in time is something like this. The positions means that to update the positions, we need to find a local minimum of this function that depends on there is a composition of the 6 energy functions that I showed you before. And then we want to find some optimal vertex position configuration for that. And then the velocity has a simpler update rule, but as you can see, the bulk of the work here is in finding this local minimum. And now you might be thinking about why is this? I mean, why should I care about this complicated way of doing physics? Shouldn't this be just F equals ma? And the truth is that yes, you can start from F equals ma, but if you naively implement F equals ma, you probably going to end up with a very explicit numerical integration method like symplectic Euler, which you see here, where you compute the acceleration based on F equals ma, use the acceleration to update the velocities, you update the velocities to update the positions, and that can lead to explosions. If you have seen numerical instabilities like this before in your simulations, maybe what you need is implicit numerical integration methods, which are much more stable. They just tend to have better numerical properties, but they are a little bit more complicated to implement because they require this minimization procedure. And there's a lot of details here that I'm going to have to skip. But if you want to learn more about what I mean by numerical integration and energy minimization in this context, you can find more details in this repo. But I'm just going to skip this for this presentation. The main message here, I guess, for very mundane implementation purposes is I think we shouldn't implement force functions in our physics engines. We should implement energy functions, and then we just use automatic differentiation to compute the force. The force is just the negative gradient of the potential energy, and this can be extended to implicit numerical integration methods based on energy minimization, which can help you with numerical stability if you've had issues with that before. Just for completeness, I also want to say this is not restricted to 2D. We can also do 3D simulations. It's the same idea. Nothing fundamentally changes. The only thing that changes is that instead of triangles, we need tetrahedra in 3D. That's the minimal structure that we need to talk about shape in 3D. And also, this is not just about locomotion on fixed morphology. You can also do morphogenesis if you want. This is not about any specific examples. I'm just trying to give you some general ideas about this idea of energy minimization as some form of viewing goal-directed behavior in very basic physical systems. So I'm trying to say something more basic here that goes beyond just how we optimize the morphology, how we optimize the controller for locomotion. I'm talking about goal-directed behavior at different scales, and I want to emphasize that the physics engine already shows some basal form of goal-directed behavior, which you can think of as energy minimization. And I think this is consistent with this very interesting framework proposed by Michael Levin, scale-free cognition. And the very mundane practical implication of this, in my opinion, is that if you're going to implement physics simulations, don't implement force functions, implement energy functions and use automatic differentiation to compute the force. And I also want to say, this is not a common misconception. Whenever I talk about simulations, physics simulations, differentiability, gradients, people think that I'm talking about differentiable simulation. This is not about differentiable simulation, but it could be, and I have a paper on that, but this talk is not about differentiable simulation. You can read the paper if you want more details, but this is not about differentiable simulation. Actually, the locomotion controllers that I showed you at the beginning, those were not optimized with differentiable simulation. We can talk more about that later if you want, but that's besides the point of this presentation. I want to focus on the physics engine as a goal-directed behavior, and then you can do whatever you want on top of it. And yeah, like I said, you can find this on GitHub. It's an open source project, and you can find more info on this website. But yeah, that's it. Thank you.